Okay. Welcome everybody to this session of el Seminario Chileno de Probabilidades de Chile. This time we have the pleasure to have with us Antoine Jego from the University of Vienna, who is going to talk us about the multiplicative chaos of the Brownian loop soup.
So thank you very much. It's really a pleasure to have the opportunity to speak here today. Yeah, so today I'm going to talk about a joint work with Elia Decon, Nathaniel Brestiki, and Titus Lupu. So this work is mainly about the connection between two objects. So the first one is written here, so Brownian loop soup, and the second one is the Gaussian free field. So I will first talk about this object, the Gaussian free field. So we have a kind of picture of it here. It can be thought of as being a natural analog of Brownian bridge with the time that is now two-dimensional instead of one-dimensional. And it appears in many different contexts. It's believed and proven in some cases to be the uniform, like the universal scaling limit of several statistical physics models. So for instance, it's the case that it is the limit of the height function in Daimer model, or it also appears as the limit of characteristic polynomials of very large random matrices. So the way it is defined goes as follows. So it is, so we have a bounding domain D in the plane, and we consider a Gaussian process, which is, if you want, indexed by the points in your domain. It is centered, and the covariance of our process is given by the green function. So the green function is defined here. It's just the integral of the heat kernel, integral with respect to time. And it turns out that in 2 dimensions, the green function is logarithmically correlated, meaning that when x and y are really close to each other, then the green function behaves like this. So because of that, we see that if x is equal to y, then the variance of h at a given point is actually infinite. And so because of that, our definition is not really rigorous, and we don't have an object which is well defined pointwise. Instead, to make it rigorous, we see it as a random generalized function. So we cannot define it pointwise, but we can define its integral against any test function. And the covariance is now given by integrating the green function. Okay, so that's the Gaussian free field, and an important object that so for this talk will be the so-called Liouville measure. So this is a random measure that is formally defined by exponentiating gamma times the GFF. And so here gamma will be a real parameter between -2 and 2. So this measure is a special instance of what's called Gaussian multiplicative chaos measure, where we exponentiate any log-correlated Gaussian field. And these Gaussian multiplicative chaos measures pop up in many different places, for instance, with the Riemann zeta function, random matrices, finance, and as I will argue a bit later, planar Brownian motion. The problem with this measure is that since h is not defined pointwise, we cannot exponentiate it, and so we need to work in order to make sense of this object. Oh yeah, okay. I wanted to say that Liouville measure is actually quite special. It's a special instance of Gaussian multiplicative chaos measure because it can be seen as being the volume form of a surface uniformly chosen at random. And in that case, you have to choose gamma to be equal to square root of 8/3. So here are a few simulations of the Liouville measure. So what you can see here is the density of the measure with respect to Lebesgue measure. So it turns out that this density does not exist, but if it did, it would look like that. And we have these simulations for 3 different values of gamma. And we see that as gamma grows, the measure becomes rougher and rougher and is supported on fewer points. So now I want to explain a bit how we define such a measure. And so to do that, instead of exponentiating directly the GFF, we will exponentiate an approximation of it. So we regularize it at the scale epsilon. Then we exponentiate this guy, and we put a normalizing constant in front of it. And so this object is now really well defined because the regularized field is well defined pointwise. What's difficult is to show that as epsilon goes to 0, we obtain a non-degenerate limit. And indeed, it has been, so this has been the concern of many works in the last 2 decades, and it's now very well understood. And we can do this in this regime when the gamma is between -2 and 2. When gamma is not in this regime, we have something a bit more complicated. If you would do this normalization, you would just obtain 0. And so the limiting object is really what we call a Leuven measure. And of course, importantly, to have a proper definition, we need this measure to be independent of the way we regularize the field. Okay, and so as was a bit hinted at in these pictures, we see that the measure is really supported on very few points. And indeed, the support of this measure is what's called the thick points of the field. So these are points where the field is atypically large. So if you have a fixed deterministic point, let's say the origin, for instance, then your regularized field would be of order square root of log epsilon. Whereas if you sample X according to your Leuven measure, then the value of the field will be much larger. It will behave like gamma times log epsilon. Okay, so this is all I wanted to say about this first character, Leuven measure. And now I will move on to the second character of this talk, which is Brownian loop soup. So here is a simulation of Brownian loop soup, if you want. So what we have is a domain in the plane, and we throw many loops in our plane. So okay, on this picture, maybe you don't really realize that these are loops. But really what we have is just many loops in the domain, many Brownian-like loops. And the way this is done is via a Poisson point process. So we have a Poisson point process of loops, and the intensity measure here is a measure on loops. So it's the so-called loop measure. So I'm not going to define it precisely, but what you obtain in the end is just a bunch of like a collection of loops, of Brownian loop loops. And you have this parameter in front of your loop measure, theta. And so this is the intensity parameter. So this has been introduced by Lawler and Werner, and it's related to different objects in conformal probability, like conformal loop ensemble, Schramm-Loebner evolution, and the Gaussian free field. So it turns out that there is a phase transition when theta is smaller than a half and when theta is larger than a half. And so this phase transition can be seen by looking at the chains of intersecting loops, so the cluster of loops. And if theta is not larger than a half, then we are going to have infinitely many clusters. And in this regime, we have a connection with these so-called conformal loop ensembles. So they can be seen as being the outer boundaries, the outermost clusters. But when theta is strictly larger than a half, we have so many loops that actually you have only one big cluster. Okay, so I mean this is quite clear that there is a kind of that this picture is a bit increasing in theta, because if theta is twice as before, then you just add two independent collections of Brownian loops. So theta equals a half is really a special point and is critical in that sense. And it's special for another reason. And at this specific point, we have a connection with the Gaussian free field. And so this is the so-called Leuven's isomorphism. And so what this isomorphism says is that if you look at the occupation field of your Brownian loop soup, so what this means is that you, for every point, if you want, you look at the amount of time spent at your point. So this is, okay, again, this is not really a well-defined point-wise object, but you can make sense of it as a generalized function. Then what Leuven's isomorphism tells us is that this occupation field has the same distribution as half the GFF squared. And for this, you need to take this very specific intensity, the critical intensity theta equals a half. Okay.
Sorry, Antoine.
So that, yes.
Antoine, could you say more precisely what this occupation field is? It's like,
okay, so
it's just like an occupation density of all the loops.
So if you want, it's really the same thing as in when you have only one Brownian trajectory, you can make sense of its occupation measure. And the occupation measure is just if you integrate to measure against the indicator of a set, then this is just going to tell you how many times my Brownian path has spent in my set. Okay. And so here you do the exact same thing.
But overall,
for the overall occupation field.
Okay, thank you.
It's slightly more tedious than in the case of one trajectory, because the problem here is that you have many small trajectories. So when you add all these occupation measures, you will just find infinity. So you just need to recenter a bit.
Okay.
But yeah, so actually you have a recentering here, but on the right-hand side, you have the same story because the GFF is not defined point-wise. It is a generalized function.
Sure.
So you cannot square it neither, and you need to recenter it as well.
Okay. Thank you.
Yeah, so Lx is just the overall amount of time spent by all the loops at x, if you want. That's in the discrete, it really would be like that. And so the type of questions that we want to understand in our work is, if you want, the relationship between a Liouville measure and the loop soup. So I have this isomorphism, so I can couple my two objects together so that this identity holds. Now I define the Liouville measure associated to my GFF. And the type of question that we want to understand is, what does the loop soup look like near a typical Liouville point? So for instance, we could ask, so remember that the GFF is atypically large at such a point. So this guy on the right-hand side is very large. And so we are going to have a very large occupation field at that point. So how is it possible to obtain such a very large occupation field? Is it because of only a few loops that go through that point, but these loops go very often to this point? Or is it a bit the other extreme? Is it because we have many loops that visit the point, but each loop actually visited only a few times? So that's this kind of question that we want to understand. In other words, we have three different objects: the loop soup, the GFF, and Liouville measure. There were two connections that were really well understood. the connection between Leuven measure and GFF, and the connection between loop soup and the GFF. And now we want to understand a bit the third one, the connection between Leuven measure and the loop soup. Okay. So now, so this I will come back to this a bit at the end of the talk. And now I will talk about Brownian multiplicative chaos. And we'll see that Brownian multiplicative chaos can be seen as being the contribution of one loop to Leuven measure. So the goal here. Okay, so what's the setup? The setup is that we have a planar domain and only one Brownian trajectory in this domain. So this blue curve. And so the goal is to build a measure that is supported on thick points of this trajectory. So what does it mean for a point to be thick for this Brownian motion? So via this Leuven isomorphism, we see that a thick point for the GFF means for the loop soup that we have a very high local time. And so now we want to do a bit the same thing for only one trajectory. We want to build a measure that is supported on points that have been visited unusually often. So this has been done, so first by Bas-Burdi and Koshnevisan in a restricted regime where, so we had the parameter gamma before, and gamma had to be small enough. And then this has been extended to the whole subcritical regime simultaneously in these two papers. And I will present you my approach to this problem. So again, here Lx is going to be the local time at x, but now again, it's for only one trajectory. Okay, so this is just the heuristic so far. And so we want to build a measure where Lx is atypically large. So via this kind of isomorphisms, such as Leuven's isomorphism, we can see the square root of Lx as being approximately log-correlated field. So it's natural to try to build a measure like this by exponentiating the square root of the local time. That's a natural goal. Okay, and so we have the exact same problem as in the Gaussian setting. Lx is not well-defined, point-wise because for a given x, the path will not visit that point. So we need to do a sum of a regularization procedure to define this subject. And so we do it as follows. So we define Lx epsilon as being the local time of a circle. So this time, this one is a well-defined object because of the circle will be visited maybe. And then we define this object here. So what is this? We just take e to the gamma times the square root of the local time. There is, okay, this 1/epsilon. So this is just because the perimeter of the circle is of order epsilon. That's just for that. And then, as in the Gaussian setting, we have a normalizing constant in front of it, epsilon to the gamma squared over 2. But since we are in a non-Gaussian setting, the constant that we need is slightly different, and we need to add this logarithmic correction to our normalizing constant. And so the claim is that this sequence of random measures converges as epsilon goes to 0. And this is valid for the whole regime gamma smaller than 2. So the output of this theorem is the construction of a multiplicative chaos for a non-Gaussian log-correlated field. And so this field is really the square root of the local time. And this measure is now phrased, it's now called Brownian multiplicative chaos. Do you have maybe questions about this this statement?
Just a stupid one to see. So I would usually put 1 over epsilon square just to be naive, no? Because this is like the measure of the ball. Why is it natural
Yeah.
to look at the perimeter?
Because I'm looking at the local time of the circle. I'm not looking at the disk, but I'm looking at the circle. That's why.
So does it make a difference?
So it should not make a difference. The local time of the circle is just a nicer object than the disk. And the reason is that in very specific cases, this local time would be exactly an exponential random variable. So
okay,
for instance,
and you know the law, I imagine, of what is inside given the local time, no?
So you approximately, as epsilon goes to 0, the law of the local time is exponential. But and actually so as a process evolving with epsilon, the square root of the local time is approximately a Bessel process with dimension 0.
Okay. So, but it's not exactly, no? So you don't have like, it is not
So it's not exactly
Markovian?
No, so it's not Markovian. It is Markovian only in specific cases. So for instance, if your domain is a disk and you look at circles that have the same center as your disk.
Okay.
Then you have birotational invariance of the Brownian motion. This is Markovian. Whereas it would not be the case if you are in a general domain and so on.
So up to this moment, also another question, there is no uniqueness in the sense that it doesn't matter which approximation you are using. You get the same final measure?
So, okay, so now there is a uniqueness statement because, for instance, the 3 papers that I mentioned, so these 3 papers use different approximations, but it is proved that they all lead to the same object. And I have a paper that gives an axiomatic characterization of this measure. So so this paper shows basically that you cannot have a different object.
But you could have like approximations which do not converge, no? Or that is not possible?
Yeah, maybe it is possible, but I mean, if it does not converge, you might not have chosen your approximation properly, I guess.
Okay.
Okay, what I mean is that for any reasonable approximation, you would obtain the same object.
Okay. Perfect. Thank you.
Okay, and okay, I will come back to this actually in the next slide. So you can see here 3 different simulations of this object. 4 for 4 different values of gamma. So so the domain is a square. The starting point is the middle of the square, and what you can see in blue is the trace of the Brownian motion, so the underlying Brownian trajectory. And then you have a measure that really lives on this trajectory. Okay, so and so we have a deep understanding of the path viewed from a thick point. That's the content of this theorem. So what it says is that if roughly speaking, you condition your path to be thick at the point x. So if you condition x to be, if you want a typical point, like typically sampled from your measure, then the path will look like that. So it is going to be decomposed into 3 different pieces. The first one is just a path that is conditioned to hit your point before leaving the domain. The last part is just a path that starts at x and that is killed when it exits the domain. And then the middle part is a bit more complicated. It's an infinite collection of excursions aware of your point. So you have and these excursions are distributed as a Poisson point process, where the measure is given by so a parameter A times an excursion measure. And this parameter A is related to the parameter gamma that we had before. We are taking e to the gamma square root of the local time. And A is related to gamma by this formula. And actually, this theorem, when you write it properly, it characterizes the law of the measure together with the path. So this gives you as well a characterization of your object. And this characterization does not rely at all on your approximation. Okay. So now I want to draw some comparisons between.
Sorry, Antoine, just a question before. Where was the gamma appearing here?
Yeah, so here gamma is, so you had this parameter A.
Yes.
So A, if you want, is the strength of your Poisson point process of excursions. And A is equal to square root, no, to gamma square root of 2. Sorry.
Okay. Thank you. I hadn't seen Thank you.
That's, yeah, that's the link. Okay, so what I've done in this slide is that on this column here, I have properties about these so Brownian multiplicative chaos measures. And on this column here, I have properties about Leuven measure. And what I want to argue, so okay, so and I recall here that Leuven measure is e to the gamma times the GFF. And what I want to argue is that these measures are like share striking similarities. For instance, the first moments are explicit, and they are they have the same flavor with the conformal reduced to the power gamma squared over 2. So in the Brownian setting, we have the green function in front of it, and this guy is here because okay, so yeah, okay, so this guy is here because our measure is supported on our Brownian trace. So these two measures are both conformally covariant, and the formula that you have is the same in both cases. The dimension, the carrying dimension of your measure is equal to 2 minus gamma squared over 2 in both cases as well. But actually, they cannot be equal at all because Liouville measure sees the whole domain, whereas in the Brownian setting, we had a measure that is supported on the Brownian trace. And what our article with Elie, Nathanael, and Titus in particular does is that it establishes a concrete link between these two objects. And so now I want to talk about this work. So this work will be about the multiplicative chaos of the Brownian. So just a reminder, so that's a simulation of Brownian loop soup, and Brownian loop soup is an infinite collection of Brownian-like loops. And okay, so I will denote it L theta, and so L theta is just a collection of loops. So here, these guys are loops. And we have this intensity parameter that was appearing in front of the loop measure, in the intensity measure. And when theta is equal to a half, when theta is critical, the occupation field of the loop soup has the same distribution as the square of the GFF. And so the first question that now we want to do is that can we define a Brownian chaos associated to this loop? So can we define e to the gamma times the square root of the local time of this loop soup? And when theta is equal to a half, so at this spatial intensity, do we recover the hyperbolic cosine of the GFF? Okay, so here it's a bit a pity because I should have written something more. So when you take e to the gamma times the occupation field of the loop soup at the critical intensity, it's natural to expect that you will find the same thing as exponentiating the absolute value of the GFF. And this is the same as taking the hyperbolic cosine of it, because this is an object which is not well defined pointwise. So the exponential is supported on points where the field is extremely large. So it's either plus infinity or minus infinity if you want. So that's why we have this. That's why we expect to have this connection. Okay, so how do we define a Brownian chaos associated to this? So so far I talked about Brownian chaos for only one trajectory, but it's not difficult to extend this definition to finitely many of them. So a very natural try is to apply a cutoff to restrict our collections, our collection of loops to only finitely many loops, to define a chaos associated, and then to let the cutoff go away. So that's the strategy that we are going to use. And again, in this whole story, we'll have two parameters, the intensity parameter and the thickness parameter. So gamma and A. So the cutoff that we use is, so it's, for us, it's really important to choose it wisely because it makes computations easier, as I will show in my very last slide. So you kill each loop independently of each other at rate k. So meaning that the probability for a loop to be killed is just given by 1 minus exponential of minus k times the duration of the loop, which is itself random, of course. And then you consider the collections of loops that have been killed. And so when k goes to infinity, you are going to recover the whole loop soup. So now we can define a Brownian chaos associated to this collection. So if you want, this is just a measure on peak points of this restricted collection of loops. And so our main theorem is that if you normalize it properly, so you divide by log k to the power theta, then this has a limit as k goes to infinity. And so really, this measure is the multiplicative chaos associated to the loop soup. And so when theta is equal to a half, the measure is so corresponds to the hyperbolic cosine of the GFF, which is exactly what we wanted. And when theta is not equal to a half, we have something which is a bit different. It's a new object that was not defined before. So do you have questions about this statement?
Yes, I do. So in this statement, I'm nitpicking, but it is the same. So you have equal in distribution, but is it the same Gaussian free field from which you are doing the coupling?
Yeah, exactly. Okay. Yeah, so we have this stronger statement. So we can couple the three objects together, so that all the pairwise connections are satisfied.
And a second one, if I give you like this MA theta, can you recover the local time?
Yeah, so that's a good question. So this I mean, from the Gaussian theory, it's really natural to expect this, but we have not proved it. But yeah, it should be true. Okay. And so now the questions that we wanted. Okay, so now we have all the objects that we need to answer the previous questions that we had before. So let me sample a point Z according to my measure. So Z is going to be a typical thick point of my loop soup. And remember that I wanted to understand a bit how many loops actually visit the point Z. Is the thickness coming only from very few loops, or is it coming from many, many loops? And if it is because of many, many loops, is it because they have all a typical local time, or is the point also thick for the individual loops? And so what we show is that we have infinitely many loops that visit the points, that visit the thick point. And we have an understanding of the thickness. So each loop is actually thick. And if we have an understanding of the distribution of the thickness of the loops. So if I denote AI the thickness of the ith loop that visits my point Z, then the AIs are distributed as a Poisson-Dirichlet distribution. So they sum up to A. So let me recall that A is this guy. So we had a gamma, and so A is gamma squared over 2. So their sum is equal to A, and they are distributed as a Poisson-Dirichlet distribution with parameter theta, and so theta is the intensity of the loop. And if you want, a direct consequence of this is the existence of points that have been visited infinitely many times by infinitely many loops. And I'm not sure that this was even clear before our work, or maybe not even not so easy to show. And moreover, if we condition on the respective thicknesses, then we know the distribution of each loop. And so each loop is distributed as the concatenation of the excursions in this Poisson point process. And so this Poisson point process is the exact same one that we saw at the beginning when I was talking about thick points of one trajectory. So we have many excursions. We concatenate all of them. This gives us a loop. And this is exactly what you need to do to recover the loops that visit your point. Okay. So I will finish my talk with 2 more slides. The first one will be about the identification of the measure when theta is critical. And so I want to argue that this is actually a difficult problem. And I already alluded to this because to make sense of Legendre isomorphism, you need to recenter both sides of the equation. And so, as I said, on the left-hand side, this is because you have way too many loops. And on the right-hand side, it's again because the GFF is not well-defined pointwise. So squaring a generalized function does not make sense, and you need to recenter the object. And so you have you obtain on the right-hand side what's called the Vic power of the GFF. And for instance, it's not even clear that the hyperbolic cosine of the GFF is a measurable function of the Vic square. So what we do instead? Okay, so what I wanted to argue here is that Legendre isomorphism is not enough in the continuum to show the identification of the measure. But in the discrete, we don't have this problem at all. In the discrete, you don't need normalization, and the identity is true pointwise. So what we do is that we take a detour, and we show that our multiplicative chaos measure of the loop soup describes actually the scaling limit of the set of thick points of random walk loop soup. So we have a construction of the measure that is done from the discrete. And the corollary of this construction is the identification that I mentioned before. Do you have questions about this? And my last slide will be about the exact solvability of the model. So I want to recall that we chose to define our measure via loops that have been killed at rate k. And so, of course, this specific cutoff should not really matter, because any cutoff should yield to really the same universal object. But then, if you want to prove things, it's easier to pick this very specific cutoff. And I think this is really something that we kind of discovered a bit by chance. So let's see. So you define this quantity here. So this ck of z prime. So you just integrate the hit kernel, and then you have this killing in front of it. And the claim is the following. So at the level of the approximation, we have very neat formulas for quantities associated to our measures. And so, for instance, if we look at the first moment of the measure, this first moment has this very explicit formula. So what you have is the conformal radius to the power a, or conformal radius to the power gamma squared over 2. And then in front of it, you have a function f evaluated at this ck times the thickness a. And f turns out to be a very nice hypergeometric function, or can be expressed in terms of a hypergeometric function. But if we had chosen a different cutoff, for instance, we could also say that we want to select only loops that have a diameter larger than epsilon. Then the expression that we would obtain for the first moment would not be as nice. So this is just so from like a technical point of view, this is a very nice feature of this specific cutoff. Thank you very much for your attention.
So thank you very much, Antoine. And I propose that we unmute ourselves to thank our speaker. So are there any questions? I'm going to try to see. So I had quite a few, but what you were discussing about the permanent field, do you have? Can you identify? Do you know what is this permanent field? Does it have some conformal properties? Oh.
Yeah, so this I'm not so aware of. So if you, so it's a bit okay. So you have this isomorphism, and when the intensity is not equal to a half, then the field that you obtain is not a Gaussian squared, but is what's called the permanent field. And so in the discrete, this is quite well understood. And then I'm not so aware of the theory in the continuum. And I don't know if okay, I'm okay. So I don't know so much about this. It's just that the intuition behind it is that you really are taking the exponential of the square root of the permanent field.
Okay, but this is not like a mean zero type of field, or is it? In a certain way, we would expect that somehow you can assign signs to this story, like for the GFF.
Yeah, but okay. So permanent fields are the permanent fields are really the Gaussian squared. So in the continuum, you would need to recenter it, but it's not the GFF itself. It's the square of it.
So you don't have like a GFF type of field. I mean, not that it's Gaussian, but just a field which has mean 0, whose square is.
No, I don't think so.
And do you expect that there exists one, or it shouldn't?
Yeah. So okay. So this is a very good question, and so okay. So this might be the direction of future research, and we are a bit thinking about this, but so far it's really not so clear for me. And okay, first direction that we could try, for instance, to define the signed version of our measure, because here we really don't see the sign of the GFF, and you could try to restrict yourself to the, for instance, positive clusters.
Yes.
Which would give you only Liouville measure instead of the hyperbolic cosine of the GFF when theta equals a half. So this is something that we plan to do actually.
And okay, so you have a lot more questions, but let me and if you do the imaginary story here, can you make sense of
yeah? So okay, so
putting imaginary gamma.
So yeah, so now we have a way of doing it, which is a bit different from this story actually, because so far we can do it in the L2 phase, and extending it to the whole like I-shaped domain is not as simple. But to do this, the first step is actually to expand the chaos with respect to gamma, because if you are able to make sense of such an expansion, then for free you can define it when gamma is not real.
Okay, see, so you are looking at the whole complex plane.
Yeah.
Yes. So maybe the last one before I monopolize this. But what is the importance of so I take a loop soup, like you have a lot of loops, and then I take out, and I'm looking at this exponential, and I take out just one loop, a big one. How does this measure change? How this?
Yeah. So you could also do the other procedure, so which is you have adding one exactly, and I think it's really the same thing in the end. And the two are related. So you can make, okay, actually there is so I think what you're going to have is, if you want, now you are asking about points that are thick for the combination of two different objects. And what you will have is two types of points that are thick only for the loop soup, and points that are thick because of the interaction of these two two objects.
Yes.
And then the contribution of each of these guys will itself be random. So what okay, and so for I've made this kind of heuristic picture, very precise actually, in one of my paper, which is called the characterization of Brownian multiplicative chaos. And in that paper, I'm exactly doing this for finitely many trajectories, but you can extend this to the loop soup as well.
So there are some interaction stories, because it's not, for me, yes, from the point of view of the GFF, it's not clear in a certain way.
Yes, there are interactions between the two. So and for instance, already when you have only two Brownian trajectories, you already have this story of points that are either thick for only one trajectory or thick for actually both of them. And these two types of points contribute the same amount, if you want, to the overall measure.
Yeah, but because in a way you can, so this Poisson point process of excursions, you can put it from one to the other and they are the same, you know? So they have the same weight if you consider that this Poisson point process is just from one, just completely in this other, or in a mix of both.
Yeah.
Okay, I see. Sorry. So is there any other question?
I have a question.
Yes.
So in the first part of your talk, you mentioned that, the construction of this Brownian multiplicative chaos, which is kind of concentrated on these thick points of just the Brownian trajectory killed when it reaches the boundary. So I was wondering if you could do the same, but instead of with one trajectory until it hits the boundary, if you could just wait until it somehow covers all of the domain. So maybe take like a small sausage or whatever, and you try to do the same, the local occupation time field, whatever.
Yeah, so this is so it depends a lot on the way you stop your trajectory, because it's a very natural question, and this is really related to like cover time type of questions, and there is like a whole list of paper actually that are concerned with these questions, especially by Marek Beskup and Yoshihiro Abe. But I think what you obtain is I'm not sure that you directly obtain the Gaussian free field, because for or Leuven measure, because for instance what they do in this paper by Abe and Beskup is that each time the Brownian path touches the boundary, then it is resampled like uniformly on the boundary, and it starts again from there. Actually, they do this for random walk, but so there you have much more symmetry, and so if you so I'm just saying that I think these are kind of two different stories, and maybe a big part of this story is how you allow your Gaussian free field to continue in your domain.
Okay.
You could certainly have like, for instance, a Brownian motion on a sphere and ask the same question. Yeah, and okay. What I can say is that if you have a Brownian motion on the sphere and you stop it after a time that is close to its cover time, for instance, with like an epsilon sausage or something, you can define a bit similarly an associated chaos, and then it's very natural to try to understand what this chaos does when you let epsilon go to 0.
Okay, but it's not very well known yet, right?
No, it's not. It's not very well understood so far.
Okay, thanks.
So are there any other questions? So if not, I propose that we thank the speaker again.
Thank you.
Thank you.
And that we cut the record.